Hello everyone. Today we're going to look at the Fundamental Theorem of Calculus Part 2, but this time when the upper limit of integration is a function of x. And if we look at the to do now problems, notice that we define the function g of x in two different ways. The first one, the upper limit is x. Notice it's the definite integral from 1 to x of cosine t dt. That we discussed in the previous lesson. But what would happen if the upper limit was a function of x? So in number 2, notice that the upper limit of integration is x squared. Okay, let's take a minute to copy these down and think about them. What would be the answers? In both problems, we would like to get the derivative of g. Okay, so take a minute and see what you can do with those. All right, well, if we go back to number 1, we know that by the Fundamental Theorem of Calculus Part 2, that our answer should just be the derivative of g is simply cosine, but we replace the t with an x. All right. And to convince us of that, this is what we discussed last time. If we actually anti-differentiate this function, and we know that the integral of cosine is sine, but we leave the t there because it's with respect to t, and then use the first fundamental theorem of calculus, we substitute the x first, and then the 1, and subtract. This would be our closed form for this function g of x, but when we differentiate it, we get the derivative of sine x is cosine x, and the derivative of sine 1 is just 0. So we're just left with cosine x. So if you recall from the last lesson, we said that, and we're going to re-summarize, if f of x is a continuous function on some open interval I, and a, which will be the lower limit of integration, is in I, then we can define a new function and we could call this new function anything. In the last lesson, I called it capital F of x. Here, I called it g of x. We could call it h of x. We could call it anything. Then we define a new function g of x, which is the definite integral from a to x of f, but we don't put an x, we put a t, because the upper limit of integration is x, dt. This is called the area accumulator. G accumulates area under the graph of f from a, which is some number in the open interval over which f is continuous, to some number x. We call this the area accumulator. And what's very special about it is that whatever this function is, whether we could integrate it or not, its derivative would be f of x. Here, the derivative is f, but we replace the t with an x. Okay, very simple. And we don't have to actually anti-differentiate. We know its derivative is f of x. Now, in the next problem, number 2, let's do it the same way as we did number 1. Let's actually anti-differentiate it. So the integral of cosine t is still sine t from 1 to x squared. We use the first fundamental theorem of calculus. We get sine x squared minus sine 1. And this would be the closed form for g. But when we differentiate it, here we have to use the chain rule. So we differentiate the outer at the inner. So we differentiate sine, which is cosine, at x squared, times the derivative of the inner. But the derivative of sine 1 is 0. So if the upper limit of integration is a function of x, how can we get to this last step without going through all of this work? We replace the t with x squared and multiply by the derivative of the upper limit of integration. So let's write this down as, okay, so this is number 1. Now this corresponds to number 2. If u is a function of x, let's call it h of x, right? Then, and if we have that g of x is the definite integral from a to u, which is h of x, of f of t dt. Now, this is a very strange area accumulator. It rarely appears in the free response, but it did happen one year, which I will show you. Then, the derivative of this function would be f of u, which is f of h of x, times the derivative of the u, which is the derivative of h. And that's the chain rule. So, all we have to remember is that we replace the t. Okay, so I'm going to circle it. We replace the t with whatever u is, no matter how long it is. We replace it in the function f, and then multiply by its derivative, which is illustrated in number 2 in the Do Now. So let's take a look at a few problems that have appeared on the AP. Derivative. Oops. So I'm going to write out a few problems. Some of them are straightforward. Okay, so 3 says, oh, wrong color again. 3 says the derivative of the integral of 1 to 1 over x of cosine of t to the 4th minus 1 dt. So now we wrote everything in one line. If a function is defined this way, what would be its derivative? So that's one way we could write it on one line. Number 4, the derivative of the definite integral from 4 to 3x squared plus 1 of the square root of e to the t plus 1 dt. Okay, we could answer each of these in one line. Number 5. If capital F of x is defined to be the integral from 1 to x cubed of the square root of t squared minus 1 dt, find the derivative of capital F. So the number 5 and number 3 say the same thing, but in different ways. Okay, and then number 6, if little f of x is defined to be the definite integral from 1 to 3x squared of the square root of t squared plus 1 dt, find the derivative of f at -2. Okay, so that one is a little bit more involved. And finally, 7. All right, now this one's a little different from 3 and 4. Evaluate the derivative with respect to x of the integral from x cubed to 5 of t to the 4th plus 1 to the 1/3 dt. Okay, so take a minute and copy these down, and let's see what we get. Okay, let's begin going over these. So, by what we just discussed, notice that the upper limit of integration is a function of x here. Oh, Let me just get this going here. I have to do it in green. See, does it work? No, it's not writing. Well, anyway, the upper limit of integration is a function of x. So we replace the t with 1 over x. So our answer is cosine of 1 over x to the 4th minus 1, and then multiplied by the derivative of 1 over x. Well, 1 over x is really x to the negative 1. So its derivative is negative 1x to the negative 2. And that's our answer for that question. Okay, of course, we could write it as negative cosine of 1 over x to the 4th minus 1 all over x squared. But this is a fine answer over here. Okay, then this is the upper limit of integration. I was trying to underline, but it doesn't work. Okay, and it's a function of x. Now, in the next one, this is a function of x, and we're going to differentiate this integral. So our answer would be the square root of e, but we replace t with 3x squared plus 1. That's the exponent. We carry down the plus 1 times the derivative of 3x squared plus 1, which is just 6x. And there's our answer. So these are really quick. All right. Now let's look at number 5. So capital F of x is defined to be the definite integral from 1 to x cubed of this function. So its derivative would be the square root. We put the x cubed for the t. So it's x cubed squared minus 1 times the derivative of x cubed, which is 3x squared. And of course, you could write that as the square root of x to the 6th minus 1 times 3x squared. And that would be our answer. Number 6, we do the exact same thing, but whenever we want to find the derivative of a function at a point, we first have to find the derivative of the function in terms of x and then substitute the point. So the derivative of this function, again, replace the t with this. So we have, so the derivative is 3x squared plus 1, and the square root of that times the derivative of 3x squared, which is again 6x. Okay, and of course that could be written as the square root of, now of course remember the rule for exponents. When we have multiplication in the parentheses, we bring this exponent to each factor. So 3 squared is 9, and x squared cubed is, oh no, this is x squared. And x squared squared is x to the 4th plus 1 times the 6x. And that's our answer for that question. Now, if we take a look at the last one, how is the last one different from the others? Notice in the last question, the upper limit of integration is 5, and the lower limit of integration is a function of x. And we know this to be the other way around. So what we will do is, and what's nice is that we could always flip the limits of integration. But when we flip, we negate the answer. And the negative 1 can be factored out of it. So the negative 1 could be factored out of the derivative, and we proceed in the same way. So we replace the x cubed with just the t. So the derivative of this equals x cubed to the 4th plus 1 to the 1/3, and we multiply it by the derivative of x cubed, which is 3x squared. And of course, this can be written as x to the 12th plus 1 to the 1/3 times 3x squared. Okay, and that's our final answer for that question. Now I wanted to share a problem with you. One free response question that appeared on the BC exam one year that had this function defined in a certain way, where the upper limit of integration was a function of x. Let's take a look at it. So I use this AP problem every year when I teach this lesson. We're given a graph of f as a function whose domain is on the closed interval from 0 to 5. So notice that f is a function whose domain is from x equals 0 to x equals 5. And this is the graph of f. Okay, now h of x is a function defined to accumulate area under f from 0 to this upper limit of integration, x over 2 plus 3. Now, that year, many students didn't realize that the only way h could accumulate area under f is if we start from 0 till 5. We can't have any number except from 0 to 5. So if we take a look at part A, part A says, okay, and this is what was very, very interesting. Part A says, find the domain of h, which most students weren't able to do because they were never asked to do so. The upper limit of integration, x over 2 plus 3, has to be, the least it could be is 0, and the most it could be is 5. So if we could solve for x here, we have the domain for h, which is not given explicitly. So what we'll do is we'll subtract 3 on all sides, which is negative 3 is less than or equal to x over 2 is less than or equal to 2, and multiply everything by 2. So we get negative 6 is less than or equal to x is less than or equal to 4. So this is the domain for h. If x is a number between negative 6 and 4, the upper limit of integration will be a number between 0 and 5. All right. Now the next question says, find the derivative of h, and that's where our topic comes in. So to get the derivative of h, we substitute x over 2 plus 3 for f, and multiply by the derivative of x over 2 plus 3. Now, x over 2 plus 3 can be thought of as 1/2 x. We don't want to use a quotient rule here. The problem's hard enough. So this is f of x over 2 plus 3 times 1/2, since the derivative of 1/2 x is 1/2. All right, that's the derivative of h. Now we want to get the derivative of h at 2. And remember, just like in the other problem, we have to get the general derivative rule and then substitute the number. So when we put 2 in for every x, we get f of 4 times 1/2. And if we look above on our graph, f of 4 looks like it's negative 3 here. So this is negative 3 times 1/2, which is just negative 3/2. And that would be our answer for that piece. Okay, now here comes the interesting part. It says, at what value of x is h of x a minimum? Show the analysis that leads to your conclusion. So here, when we ask to find the minimum value of the function, we have to use the closed interval test. So let's take a look at the next page. Well, in order to use the closed interval test, we first have to find out the candidates to test. Of course, we're going to test 0 and 5. those are the endpoints. We always check those out. But we have to find out the points at which the first derivative of h is 0. So we have to set the first derivative of x to 0. And if we look at the equation for the first derivative, the equation for the first derivative of h was f of x over 2 plus 3 times a half. Now this is interesting. In order for this to be 0, then we could multiply both sides by 2, and we have f of x over 2 plus 3 equals 0. Now we have to use a little bit of creativity and ask ourselves, when is the graph of f equal to 0? Well, the graph of f is equal to 0 when x equals 2. So we know that f of 2 is 0. So if these two conditions hold, we can conclude that x over 2 plus 3 must equal 2 for that to so that the domain element is 2. So if we subtract 3 and multiply by 2, our critical value here for h would be -2. So now we use our closed interval test. And with the closed interval test, we make a list of the endpoints and the critical value. So we have 0. Oh, actually, we have to use the domain of h. So we don't use 0. We use the interval that we found, -6 to 4. So I'm going to put it down as 4, -6, and -2, because this is the domain for h. And h of x, I'll write it here, is the definite integral from 0 to x over 2 plus 3 f of t dt. So now let's look at it. Let's substitute the x in each of these. So this would be, h of 4 would be the definite integral of 4 over 2 plus 3 dt. The next one would be the integral from 0 to -2 over 2 plus 3 dt. Oh, I forgot to put f of t here. Let me just write that down. Of f of t dt. This is f of t dt. And this is the integral from 0 to -6 over 2 plus 3 of f of t dt. Now let's evaluate these. This is the definite integral from 0 to 5 of f of t dt. This gives us the integral from 0 to 2 of f of t dt. And this gives us the integral from 0 to 0 of f of t dt. Now the one that's the easiest is the last one, because we know that when the upper limit equals the lower limit, the answer to the integral is 0. Let's take a look at the second one. The area accumulated under f from 0 to 2 is certainly positive. And that's because the graph of f is above the x-axis. In the next one, we're looking at the total area accumulated from 0 to 5. So from 0 to 2, we see that the area is positive. From 2 to 5, the area is negative, but there's no more area below the x-axis than there is above the x-axis. So the total area accumulated would be negative. And they did say to justify. So we would say, since the area below the x-axis is greater than the area above the x-axis. So where does the absolute minimum occur? The absolute minimum occurs here at x equals 4. Now notice they didn't ask us to get the absolute minimum value because we can't. So the answer to the last question, and I'll put it up here so I don't use another page. So the absolute minimum of h is at x equals 4, because we know that that value is a negative y value, which is certainly less than a positive y value and a 0 y value. And that takes care of that AP. All right, I hope that that clarifies it. I know this is very complicated, but it just takes a little bit of time to get used to it. All right, have a great day, everyone.